Okay, hi everyone. Welcome to the second video of the fifth week when we will discuss link bridging or measures of link importance in a network. Before we start with that, I have a short announcement that I forgot to tell you in the first video. Regarding the submission of homework 1, obviously you will not come to the faculty to submit the hard copy, so please just submit an electronic version to Chilnica, and I will print out the reports for you. Just please make sure that, for instance, you submit a PDF and that all the fonts are included so that everything will print out nicely. Okay, so the topic for today is importance of links in a network. If you remember, last week we already discussed measures of node importance, so how to find the key nodes in a network. And this is to some extent related to the current situation with this coronavirus, because measures of node importance would highlight the nodes that can easily spread disease to other people. So for instance, the simple degree centrality will find nodes that can easily spread the disease to their neighbors in one step. For instance, closeness centrality will highlight the nodes that are kind of in the center of the network, so they can spread the disease to the entire population in as few steps as possible. Many of these measures of node importance can be easily generalized to link importance, and today we will discuss two of such measures. One will be betweenness that we already introduced for node importance. This can be easily generalized also to links. And the second measure that we will look at is link embeddedness, which is basically a generalization of the clustering coefficient for nodes to links. So let us now move to the slides. Wait a second. Okay, so measures of link bridging are trying to find the most important links in a network, and as I said, we will look at measures that are based on betweenness centrality, which I will call link bridging measures, and also link embeddedness measures that are a generalization of the clustering coefficient, also sometimes called topological overlap measures, particularly in the community detection literature. And similarly as for node centrality, we will introduce different measures and look at which links do they highlight in the Lpp Bus Network that we already introduced. So the first measure is simply the link betweenness. If you remember, in the case of nodes, node betweenness was measuring what fraction of shortest paths between every pair of nodes goes through one particular node. In the case of link betweenness, the definition is exactly the same. The only difference is that you measure what fraction of shortest paths go through a particular link, not node. So in a way, the measure is saying that the most important links are those that are in some way between other nodes, between different parts of a network. So let G sub ST denote the number of shortest paths between nodes S and T, and let's G S sub T with the superscript ij count the number of these paths that go through some particular link ij. Then the measure is exactly the same as in the case of node betweenness. You simply measure the fraction of shortest paths that go through link between nodes I and j. The only important thing is that when you select the start point and the target point, or start node and the target node for your shortest paths, you do not include nodes I and j, because that would be trivial. Here in this picture, on the left-hand side, you can see link between us for some toy network. And if you remember, already for node between us, we said that sometimes people argue that the measure is not most appropriate in some circumstances due to the fact that it's only measuring the shortest paths between the nodes, only geodesic paths. Because, for instance, if you think about communication or disease spreading, the disease would not always spread through the shortest path, but might also include longer paths. For that reason, the link between us can be generalized in order not to take into account only the shortest paths, but to take into account random walks between pairs of nodes. And so this will take into account all paths of all possible length. And of course, you would weight different paths based on their length. So shorter paths should still get higher weight than longer paths. So now that we have introduced the link between us, let's look at what are the results for the Lpp Bus Network. Here the figure is showing you the network with the thickness of the links corresponding to the importance of that particular link or to the to their link between us. Just a second. How do I do this? Do not disturb. And we can see different strong paths extending from the center of Ljubljana to different parts of Ljubljana, as we would expect. It turns out that the highest between us link is between bus stop Vič and Stanin Dom, which is near our old faculty location. So this is basically it regarding the between us. If we move on and look at a simple adaptation of link between us, which was introduced 4 years ago and called link-bridgeness. So the idea of this measure is that important links should be bridges between different parts of the network. If you remember already when we introduced node between us, we said that in some cases it does not give us the most intuitive results. So for instance, if we look at this toy network at the bottom left part of the slide, there is a green node that seems to be most between different parts of the network. This seems to serve as a bridge between different parts of the network. However, its between us is lower than the between us of two local centers shown here with red nodes. Because all the shortest paths that go through the green node obviously also go through the red nodes, and there are additional shortest paths going through red nodes. For instance, the one going from this node to that node. In a way, you can say that the between us centrality, instead of highlighting only global bridges, it also highlights some local centers in a network. These are these red nodes, which in some cases might not be desirable. In order to correct for that, there is a very simple adaptation shown on the formula above, which is basically the same formula that we saw on the previous slide, with the only difference that when you select the start and target nodes for your shortest paths, you not only do not include nodes I and j, but you also do not include the nodes that are either in the neighborhood of node I or in the neighborhood of node j. Here the neighborhoods are denoted with this large gamma. Otherwise, the measure is exactly the same. So to connect this bridgeness, which is shown here with sigma bar, and betweenness, which is shown here with sigma, the only difference is that you do not include the shortest paths that go through between the nodes that are neighbors of either node I or j. So you can use a very similar algorithm as for computing link betweenness. If we look at the results, it's probably looking at the picture, it seems very similar as the results that we got for link betweenness. There might be some small changes, but not very obvious. So maybe this network is not the best example to show the difference between betweenness and bridgeness, but you can look at into this paper where they give some relevant examples of networks where both measures will give you different results, and they are arguing that in that particular scenario, link bridgeness is more appropriate. So this is regarding the betweenness and bridgeness, trying to measure which links are some brokers, bridges, or between different parts of the network. So to move on, I also said that we will be discussing measures of link embeddedness, which are a generalization of the clustering coefficient for nodes. And basically, these measures are saying that important links are those that are well embedded in the network, well embedded between different parts of the network. So the formula is actually very simple, but let's move to the blackboard and try to derive this formula there. So let me make this larger. Okay, so imagine that we are trying to characterize the link between nodes I and j. So let this be my node I and my node j. Both of these two nodes also have some other neighbors. Let's put 3 neighbors here and 2 neighbors here. Now, to measure how embedded a link is within the network, similarly as for the node clustering coefficient, you simply measure how many triangles the link is included in. In this case, the link is not included in any triangle, so it will have embeddedness of 0. However, if I introduce some common neighbors of nodes I and j, each common neighbor creates one triangle, and this is something that I want to characterize. So in a way, what we are measuring here is that what fraction of the neighbors of node I and j are the same. So let again denote the neighborhood of node I with gamma sub I, and the neighborhood of node j with gamma sub j. The only thing to mention here is that the neighborhood of I should not include node j, and the neighborhood of j should not include node I, because since we're measuring the importance of this link, we already know that these two nodes are neighbors of one another. But I will not use a different variable for that, just for the case of simplicity. So basically what we have is 2 sets of nodes, and we want to characterize how similar these 2 sets are. And probably the most standard measure of set similarity will be called Jacquard similarity or Jacquard index, which is basically measuring the fraction of elements of 2 sets that are the same. So imagine that we have 2 sets A and B, and their Jacquard coefficient of sets A and B is simply defined as the size of the intersection of these 2 sets. So intersection B divided by the size of their union. If we go on, we can write the union by taking the size of the union as taking the size of one set plus the size of the other set minus the size of the intersection, because it was double counted in this case. So what we get is the size of an intersection divided by the size of the first set plus the size of the second set minus the size of the intersection. And this formula here is basically what is basically the measure of link embeddedness. So if we write down how the formula would look for sets gamma sub I and gamma sub j, we will get the intersection at the top, which is basically the number of common neighbors of nodes I and j, or the number of triangles that the link between I and j is included in. Then divided, the size of the first set is simply the degree of node I minus 1, because I'm not counting this link, so it will be k sub I minus 1. Then the size of the second set will be k sub j minus 1, and again I have to subtract the intersection. So the formula that I have just written down is exactly the formula that you can see on the slides. So let's look at that. So here the embeddedness of link ij is denoted by theta, and it's simply the size of the intersection of the neighborhoods divided by the excess degrees of the nodes minus the intersection. Again, we have to decide what to do in the case when nodes I and j have no other neighbors than I and j. Notice that since there exists a link between I and j, their degree will be at least 1. But in the case when the degree of both of the two nodes is 1, this denominator here will be 0, so the measure is undefined. In that case, we will set the embeddedness of the link to 0. So if we look at the results for this link embeddedness, here is what we are getting, and you should immediately notice that we have the same problem as with standard clustering coefficient for nodes, which characterized the nodes that we would not deem the most important, usually nodes with very low degree, because they can easily have high clustering. The same is here, that the highest embeddedness node links are those that have that their endpoints have relatively low degree, so for instance degree 2. So the most important link in this case is Zalux Saturnus, and also some other links here, which we will probably all agree that these are not the key links in this network. We would expect that the most embedded links are the ones that are somewhere here in the center of the network. So in order to correct the measure in the same way as we corrected the clustering coefficient was, if you remember, there we replaced one of the degrees of the nodes, of the neighboring nodes, with some constant denoted with mi, which is maximum number of triangles over particular link. So you go through all the links, and for each measure how many triangles that link is included, and take the maximum of that. This is our variable mi here. So in order to correct the link embeddedness, to get so-called corrected link embeddedness, we will replace one of these two degrees by this new variable mi, this constant mi. So notice I still retain the largest of the degrees, so I take the maximum of the both degrees minus 1, but the smaller one is replaced by this mi. And you can look in the paper why doing it in that way properly normalizes the measure between 0 and 1. Now let's look at the results. Notice that the results are much more reasonable. Now the most important link, the most embedded link is between Posta and Consortii, which is in the center, and also other links in the center are also highlighted, and no longer, for instance, the link between Zaluk and Saturnus is as important as it was before. It's still more important than this link here, for instance, which is reasonable, but the most important links are the ones in the center. So this is basically it regarding the link embeddedness, I should maybe again highlight that same as for node importance, we looked only at 2 measures or 3 measures of link importance here, but these are not, of course, the only measures. There is a variety of different measures for measuring link importance, and again, there is no best measure, there are only different measures, and it depends on your particular scenario, your particular application, which measure would be reasonable. So that's it regarding the link embeddedness or link bridging measures. So again, I will pause the video here, publish it separately, and in the next video we will discuss the small world networks and what does that mean. Maybe I should just make a short introduction. So if you look at the next set of slides regarding the small world networks, the first thing that we plan to do is watch that documentary that I only show you the trailer during the very first lecture. So if you click on this link here on this board connected, it will guide you to YouTube where this documentary is available. It lasts a little less than 1 hour, so maybe before listening the lectures on small worlds, please have a look at this documentary. So this is it for this video. Thank you for listening.